This video is about tabular integration by parts. It's about when we use tabular integration by parts, why it works, and how to use it, our first example, and then we'll do a couple of other examples in another video. So we're going to use tabular integration by parts whenever we're using integration by parts and whenever u is equal to a polynomial. There are other times when you can use tabular integration by parts, but it's particularly useful when u is a polynomial, especially when that polynomial has degree 2 or higher. If it's first degree, it still works. It's a very fast way to get the antiderivative. But if it's degree 2 or higher, it's especially useful. And I just want to show you why. So let's say you've got a problem like this. Basic rules do not apply because we've got a product. A u substitution doesn't apply because the derivative of the inside function is just a 1/2. And that 1/2 is not going to account for that x cubed. So we have to go to integration by parts. Now remember, with integration by parts, u is the function with the simplest derivative, and dv is everything else. Since there are no natural logs, no inverse trig functions, we're going to choose u to be the polynomial. So we're going to say u equals x cubed, and dv is everything else. So create my little table. Then to fill this in, we're going to differentiate u. The derivative of x cubed is 3x squared. Don't forget to multiply by dx. And then the antiderivative of e to the kx is e to the kx. K is 1/2 this time. We have to divide by 1/2. It's the same as multiplying by 2. So you're anti-differentiating over here. According to our formula, we get u times v minus the integral of v du. So I've got 2 times x cubed e to the x over 2 minus the integral of v times du. 2 times 3 is 6, x squared e to the x over 2 dx. All right. So integration by parts tells us that this integral is equivalent to this. Question is, did it help us? Is it now easier to get to the answer for this problem? Am I closer to my antiderivative than when I started? And it turns out that with our choice of u and dv, the answer is yes. Notice that we started up here with a cubic polynomial times an exponential. Now I've got a quadratic polynomial times an exponential. It's a good thing. With a quadratic times an exponential, the powers are going down. The power went down because I took the derivative of the cubic to get the quadratic. But I still don't have a basic rule for that. I still can't use u sub, so I've got to use integration by parts again. So I'm going to let u equal the polynomial, let dv equal everything else. Take the antiderivative of dv. Take the derivative of u, don't forget to multiply by dx. And then according to integration by parts, we get uv minus the integral of v du. Now that is the value of the whole integral. So that negative here has to distribute to everything that we just came up with. That's u times v minus the integral of v times du. 2 times the 12 gives us a 24. And don't forget your dx. Distribute the negative to that term and that term. Then I look at this and I say, do I have a rule for that? No, I don't have a rule for that because of the x. U sub also does not work. So we're going to have to do something else. Again, we're going to use integration by parts. Notice the degree of the polynomial went down by 1 again, because when I took the derivative of this quadratic, I got a linear polynomial. So here's my u, and there's my dv. The antiderivative of this exponential is the exponential times 2. The derivative of 24x is 24. And so according to integration by parts, we get uv minus the integral of v du. Do we have a rule for that? Yes, finally, we have a rule, so we can finish it. If you want, you can factor out the exponential, but you don't have to. We're going to have this 48 times the 2, so that's going to be 96. Oops, not dx, plus c, and we're done. Okay, so that is an example. It's pretty long, where tabular integration would have helped us. See, with u being a third degree polynomial, I had to use integration by parts 3 times. The first time, this integral became a second degree polynomial. And then the second time, the second degree polynomial, after integration by parts, it left us with a first degree polynomial. So every time we do integration by parts, the degree of the polynomial that I'm anti-differentiating goes down by 1. So this first degree became a 0th degree. So it went from, let's look at them all. It was a cubic polynomial times an exponential, then it was a quadratic polynomial times an exponential, then it was a linear polynomial times an exponential, and then finally our constant times the exponential, and we got to finish the problem. There is an easier way called tabular integration, and tabular integration is going to allow us to do this much, much faster and much, much simpler. So here's how it works. Call it tabular because we're going to put everything in a table. U goes in this column, and dv goes in the adjacent column, and usually we leave off the dx. So u is our polynomial, write that down. dv is the exponential. Then we're going to differentiate. So we get 3x squared, differentiate again. 6x, differentiate again. 6, differentiate again. 0. You're going to differentiate u until you get 0, and that will always happen if u is a polynomial. Now, there are ways to modify integration by, or tabular integration, so that u can be any function. It doesn't have to be a polynomial, but I only use it when it's a polynomial. This is the simplest way to get to the answer when u is a polynomial. So in our class, we're just going to differentiate until we get 0, and then in the second column, you're going to anti-differentiate until you catch up with the 0, until you have the same number of rows in both columns. The antiderivative of e to the kx is e to the kx. We're dividing by k. Dividing by 1/2 is multiplying by 2. And then do it again. You're going to multiply by another 2. And then do it again. And then do it again. So you put your polynomial here, differentiate till you get 0. Put your dv over here, and we usually leave off the dx, and anti-differentiate until you have the same number of rows in both columns. So you've got 1, 2, 3, 4, 5 rows. Now on the side there's going to be a sign convention. I'll tell you what to do with these signs in a minute. So we're going to have plus, always starts with a plus, then a minus, then a plus, then a minus, then a plus. Okay, now the answer to this one is the integral of x cubed times e to the x over 2 dx is given by this. You want to multiply across this diagonal. So we get 2x cubed e to the x over 2. And then multiply across this diagonal. So you've got 12x squared e to the x over 2. Then multiply by -1 and add. Then multiply across this diagonal. And multiply by +1 and add. Then multiply across that diagonal. Multiply the result by -1 and add. And don't forget your plus c. And that's your answer. And look, it's the same answer here that we got down here. And this was a lot more work. Okay, so some students say, wait a minute, and they want to back it up, and that's why we've got the video, and that's cool. Like, how did that work? Why did that work? Let's think about what happened. With integration by parts, this first term is u times v, right? This was our u times v. What did we do in the table? If this is u and that's dv, the antiderivative of dv is v. So that's u times v minus, then we get the integral of v du. So we're subtracting the integral of this times this. Well, that times that is right there. But the integral of that times that is uv minus the integral of v du. And the integral of that is uv minus the integral of v du. And it just keeps going. So this is the first uv, that's the next uv, that's the next uv, and so on. And so eventually we get this. We would have had to do integration by parts 3 times in order to get this answer. But we can do it pretty simply with this table instead. Now, some students ask, where did this plus minus come from? The plus minus on the side came from us subtracting. Remember, our integration by parts formula looks like this. It's uv minus the integral of v du. When I substitute in what I get for integration by parts for this guy, that negative has to distribute. So I get a negative here, and the negative times that negative is going to make that positive. That's a positive, negative, positive, which is that positive, negative, positive right there. And the pattern continues. Now, I do want you to be careful about that. Whenever you're doing tabular integration by parts, this is not telling you that whatever you get here, you change the sign to make it positive. This is saying do this times this and multiply it by +1. Then this times this and multiply by -1. And this times this and multiply by +1. And this times this and multiply by -1. It's telling you what to multiply by. It's not telling you the sign of the final answer. In this one, it happened to be the case that we ended up with a positive, a negative, a positive, a negative, and then the plus c. But that only happened because all of these guys were positive and all of these guys were positive. You cannot count on that sign convention here, but you absolutely can count on it here. So just remember, this is multiplying by positive or -1. Multiply by +1, add. Multiply by -1, add. Multiply by +1, then multiply by -1, add. And don't forget your plus c. And that's going to get you the correct result every time. I'm going to make another video that does not go into why the formula works or how to use it, and there's not going to be an example of us working it out the long way. We're just going to practice some more tabular integration in the next video.